These are the answers to homework 4I. Here's the definition I would like you to know. And now on to the questions. Number 1, calculate the percent composition by mass of each element in C3H4O2. So to calculate the percent by mass of each element in a compound, you want to set up the calculation to determine the molar mass of the compound. 1 mole of this compound contains 3 moles of carbon. 3 moles of carbon multiplied by 12.01 grams per mole equals 36.03 grams. 1 mole of the compound contains 4 moles of hydrogen, so 4 moles multiplied by 1.01 grams per mole for hydrogen, that equals 4.04 grams. And 1 mole of the compound contains 2 moles of oxygen, so 2 moles multiplied by 16.00 grams per mole gives you 32.00 grams. So these are the masses of the 3 different components of 1 mole of C3H4O2. If you add those up, you'll have the molar mass of C3H4O2. To calculate the percentages by mass theoretically for this compound, the fractions are set up in this calculation. 36 out of the 72 grams is the fraction that's carbon. 4 out of 72 is the fraction that's hydrogen. 32 out of 72 is the fraction that's oxygen. So the actual calculations for carbon would be 36.03 grams divided by 72.07 grams multiplied by 100 for significant figure value, 50.00%. For the hydrogen, it's 4.04 grams out of the 72.07 grams multiplied by 100. This will be a 3 significant figure number, 5.61%. The final one, oxygen. The fraction of oxygen in 1 mole of the compound is 32 out of 72, so 32.00 grams of O divided by 72.07 grams of the compound times 100 gives you a 4 significant figure number of 44.40%. You may notice that if you add these 3 percentages up, they come out to be 100.01%. Sometimes because of differences in significant figures, the answers will not exactly add up to 100, which would be okay. These are all the correct answers according to our significant figure rules. But if you don't like that, what you can do is you can always calculate the final element by going 100 minus the percents of all the others, and then you'll wind up having answers that add up to be exactly 100%. Question number 2. Calculate the number of atoms of phosphorus present in 5.00 grams of tetraphosphorus hexaoxide. Tetraphosphorus hexaoxide has the formula P4O6. And in this particular problem, we have a sample that's 5.00 grams, and we want to know how many atoms of phosphorus. To do that, we'll need to switch the grams of the compound into moles, so we will calculate the molar mass of P4O6 and use that as a conversion factor with the 219.88 grams on the bottom, the 1 mole on the top, so the grams cancel out. We now know moles of P4O6. We're going to want to know atoms of phosphorus. So now we need to know the relationship between phosphorus and the entire compound. And if you look at the formula, you can see that 1 mole of P4O6 contains 4 moles of phosphorus. I can make that an equality statement. 1 mole of P4O6 equals 4 moles of P, and arrange that in a conversion factor with the P4O6 on the bottom to cancel out. And now I've calculated the number of moles of phosphorus. Now that I know moles of phosphorus, I can calculate atoms of phosphorus by using Avogadro's number with the mole on the bottom. If you multiply this out, it's a 3 significant figure number divided by a 5 significant figure number times a 4 significant figure number. Answer will be rounded to 3 significant figures. And so this sample has 5.48 times 10 to the 22nd atoms of phosphorus. Question number 3. A metal oxide with the formula M2O3 is 68.4% metal by mass. Calculate the molar mass of the metal. So molar mass has units of grams per mole. So if you want the molar mass of metal M, you need to know the grams of metal M and divide it by the moles of metal M. The only thing they've given us in the problem is percentage data by mass. So what we can do is we can convert that into actual mass data by assuming a 100 gram sample of the compound. If we have 100 grams of M2O3, that means 68.4 grams of it must be metal M. So to calculate the molar mass, we're going to use 68.4 grams of metal M, and we're going to have to divide it by a calculated number of moles. the number of moles are going to come from the mass of oxygen. Where does that come from? Well, if we have a 100-gram sample of the compound and 68.4 grams of it is metal M, then 100 minus 68.4 will be how many grams of oxygen there are, which should be 31.6. So this 100-gram sample of this compound is 68.4 grams of M, 31.6 grams of O. And we can now use this to solve for the moles of M. I'm going to convert the grams of oxygen into moles of oxygen by using oxygen's molar mass. And then from the formula of the compound, there's 2 moles of M in the compound and 3 moles of oxygen. I'll make an equality statement out of that. 2 moles of M equals 3 moles of oxygen, and arrange it with the moles of oxygen on the bottom to cancel out so that I can determine theoretically how many moles of M must be in that 100-gram sample. And that comes out 1.317 moles. So now I can plug that into the denominator in my little fraction up in green there. So it's 68.4 grams of M divided by 1.317 moles of M, and that will give me the molar mass of this compound, or this metal, which turns out to be 51.9 grams per mole.